Hello, we are Claudia and Jonathan, and we are going to explain how the dynamic voltage scaling works. First of all, let's make an outline about our work. First, we are going to do a brief explanation of what is dynamic voltage scaling and how it works. After that, we will show a block diagram and where is commonly DVS used. Finally, we will talk of an improvement of the basic DVS system and extract some conclusions. Well, let's start. What is dynamic voltage scaling? Dynamic voltage scaling is a method of reducing the average power consumption in embedded systems. Many systems have time-varying performance requirements. For example, a workstation requires more performance when running Spice than when running Solitaire. This is accomplished by reducing the switching losses of the system by selectively reducing the frequency and voltage of the system. Here we can see an example of when the valid data is captured. Let's take the current state of the picture as a reference for now. Think that we start a Skype conversation where latency is critical, or that we turn on the webcam and we take a selfie, where are needed a lot of operations per second. So we can try to do a couple of things: increase the frequency or increase VDD. Let's see how it improves increasing the frequency. As it is seen, increasing the frequency, we can take the valid data earlier. Let's now return to the reference case and see how it improves increasing VDD. Notice that changes are not in scale. Well, now, with increased VDD, we can also increase the frequency and we obtain the best improvement. Okay, now we change completely the problem and think that, for example, we send an email. In this case, it does not matter if it arrives in a few seconds or in 5 minutes, so we can reduce VDD and frequency. Now let's talk about power consumption. First, let's start with a normalized frequency from 0 to 1. Then, let's put in the y-axis a normalized frequency consumption. Finally, 3 different representations of VDD that could be 3 different shapes of work of 3 different single tasks. Imagine now that we start running with a very heavy application, like could be Skype, with a lot of requirements in latency and computation, so we mark the maximum performance point. Imagine now that we turn off the sound and we are only using the video channel in the Skype conversation. So we have only to deal with image. As a consequence, we can decrease the frequency because we have less requirements, but we cannot decrease VDD because we want to maintain a low delay value. Okay, now imagine that you don't want the video and you only want to make a call with your friend, turning off the video and switching on the voice, so you have less requirements. Repeating the process with applications that every time require less effort, you can finally find the curve that relates power consumption with VDD and frequency.
Okay, well, now I'm going to talk about the block diagram of a DVS system. The DVS system is mainly composed by 3 blocks: the DVS controller, the switching voltage regulator, and the core logic. The DVS controller takes information from the system about the workload and/or the die temperature. It determines the supply voltage and clock frequency sufficient to complete the workload on a schedule or to maximize performance without overheating. A switching voltage regulator efficiently steps down voltage in from a high value to the necessary VDD. The core logic contains a phase lock loop or other clock synthesizer to generate the specific clock frequency. Where is DVS used? DVS is typically used in battery-operated devices where power savings and battery run times are paramount. DVS is also used in large systems with multiple processors where power savings is required for thermal reasons. Also, DVS is implemented in cell phones, microcontroller-operated devices, etc. The following example is extracted from a paper. And here we have an implementation of a DVS system with an improvement that it's the voltage scheduler. It controls the processor speed by writing the desired clock frequency to a system control register. The temporal scheduler is the register of the deadline of a task, and combined with the estimator give the optimal VDD and frequency. The optimal clock frequency in a single tasking system is simply workload divided by the deadline time. A more sophisticated voltage scheduler is necessary to determine the optimal frequency for multiple tasks. Workload predictions are empirically calculated using an exponential moving average. And finally, the conclusions. With the right implementation, DVS can improve the energy efficiency of battery-powered processor systems by up to a factor of 10, without sacrificing peak throughput. DVS is amenable to a standard digital CMOS processor, with a few additional circuit design constraints. The dynamic voltage scaling method is a powerful technique that supports the optimization of power consumption for modern processors. Finally, the system demonstrated that when running real programs, DVS provides a significant reduction in measured systems' energy consumption, thus significantly extending battery life.